Hi and welcome to this ESS revision guide video 1.3 energy and equilibria, and today we're going to be looking at thermodynamics, equilibria and tipping points and linking this to our knowledge of the environment and environmental system. So first thing you need to know are the two laws of thermodynamics. So the first law of thermodynamics is that energy in all systems must follow this, and the first one is conservation of energy. And this is the idea that energy cannot be created or destroyed, but only transformed from one form to another. So for example, if you had 100 joules of energy going into an alarm clock, 100 joules of energy would have to come out. But not all of that is useful energy. Some of it is going to be coming out as wasted energy. And the second law of thermodynamics links to entropy. Entropy of a system not in equilibrium will increase over time. So basically what that means is it is a measure of the disorder in a system. So more entropy spreading out means more energy is spreading out and there is less order. So for example, a light bulb, the electrical energy in has a lower entropy, but then out comes from that heat and light, so this has a higher entropy. There is more disorder, energy is spreading out and being lost. And because of this rule of entropy happening, that energy transfer is never 100% efficient, as energy is used to do work and some always inevitably dissipates, normally as heat energy, which is wasted. The second law, therefore, we can look at and apply to food chains particularly. So we know that food chains only have a certain number of trophic levels, and the reason they do so is that energy transfer is never 100% efficient, because always we lose some energy as heat. And you can see here, you can calculate the energy in a system by doing this equation, which is the energy there equals Q, which is the heat energy, plus plus the work done. So we can work out the energy by doing energy is Q minus W plus the food energy added. Entropy means energy wants to move naturally from a high level to a low level. Until the universe has no difference in energy. So the universe itself is spreading out and the energy is separating. So what this means basically is if you've got something like this, the water will automatically flow from a higher level to a low level until it's equaled out, and at that point it won't ever go back upwards to the cup at the top. And life effectively is a constant battle against entropy. We need to constantly replenish high levels of energy, which we spread out to our surroundings. So if you think about the food you eat, it's concentrated energy. You eat that energy and then it dissipates because you use it as heat energy, which is lost to the surroundings. And whenever heat is released, it is high entropy as the system is becoming less ordered because that heat is spreading out and becoming less concentrated. And as a result, hot materials the heat always spreads towards cold materials and spreads out to become less. Now this has a big impact on food chains because food chains are obviously based on energy transfer. So you can see here that you might have 1,000 joules of energy going into a plant, but only 10 joules of energy then passes onto the actual primary consumer. And that is because some of that energy is absorbed, some of it is reflected, and therefore entropy is having an impact because it is spreading out to the environment. And then out of that 10 joules, only about 1 joule will actually get passed on to the next consumer because, again, due to entropy, that energy is being lost into the environment and that energy is being spread out. Now, the percentage efficiency that you need to know is energy transferred to the next level by energy received. So if I wanted to calculate that for going into the deer, I would have done the following equation where I would have done energy transferred into the next level was 10, okay, and then I would have done that divided by energy that was received, which is 1,000 coming in. So I've done 10 divided by 1,000 times 100%, and that would have given me my efficiency of. Now, within all this, this means that systems are obviously potentially at risk, and more stable systems are the ones that are more complex. And that is because if you remove a pathway from a stable system, sorry, a complex system, it will have less impact. Whereas if you remove all something from a very simple system, it might have a large on that system. So complexity means more stable, and that is a sign that comes up throughout the An example of this is tundras are very simple systems. Their populations tend to fluctuate. If one species crashes, loads of species crash. Whereas in, and another example in monoculture, something like where we've grown potatoes only. If one species crashes, then lots of then the whole ecosystem might fail as a result. So this all links to equilibria. So equilibria is the tendency of a system to return to its original state following a disturbance. So a more complex system is more likely to return to its original state following a disturbance. Whereas something like a tundra, which doesn't have much variety, is less likely to return, and therefore it's going to be less stable. So this links back to the idea of systems and the fact that systems may have to manage themselves in order to stay stable. So when a system is in equilibrium, a state of balance exists amongst all the components of that system. Open systems tend to stay in steady state of equilibrium because matter is gained but lost, and overall the systems tend to stay balanced because if you lose some energy or matter, more energy or matter comes in, so therefore it's less self. So the three levels of equilibrium we need to know about are firstly static equilibrium. This is when there is no change over time. So if these two people sit on this seesaw, they're not going to change. And there would be no change on here. And this is because the forces in the system are balanced and relationships with the components remain unchanged over long periods of time. This cannot occur, however, with living organisms because they constantly involve energy and matter exchange. So we don't get static equilibrium in living organisms. But an example of this might be something like these rocks that are piled up here. And these rocks are called a pile of scree, and these rocks, as long as they remain undisturbed, i.e. nothing comes and actually disturbs them, they will stay balanced because they'll have the forces acting on them now will be balanced, and therefore they won't necessarily collapse down any further. It's only if someone walks up these pile of scree that then you will see some of them move down, and even then the impact normally isn't great. So then living things can't do this because, as we said, matter and energy is constantly being added to systems or removed to living systems. Then we start to look at unstable equilibrium. So stable equilibrium is when a system tends to return to the original equilibrium after a disturbance. And unstable is when systems tend to return to a new equilibrium after disturbance. So if you think of it, these two pictures, stable equilibrium will be where the ball might be pushed up the side of this slope, but as long as it doesn't go too far, as soon as you release it, the ball will come back down the slope this way. So even though it's not static, like the scree rocks we were just talking about, this one is stable because the system tends to return as long as it's within a certain tolerance. Unstable equilibrium, though, tends to return to a new equilibrium after disturbance. So this one, if you push this ball either way, it's not going to come back to the middle. It's going to go down there and set a new equilibrium position. So living things and the environment we like to think are more stable in terms of equilibrium because they are more likely to return to the original position, but unstable things will change. And how is this done? Well, this is done through something called feedback loops. Systems are constantly affected by information inside and outside of them. So for example, your body temperature, if your body temperature goes hotter than 30 degrees, or 37 degrees, sorry, your body will detect that increase in temperature. So your brain, your nerves will detect it. Your thermoregulatory center in the brain detects it, and it will cause sweat to be released, which lowers the body temperature down. So effectively, going back to that diagram we just saw a minute ago, you've got that sort of level there. If your temperature goes up, the brain detects it and it will let it go up for a certain amount, but then it will have to go back down. And our bodies maintain that system, and that detecting an increase and then causing a decrease is called negative feedback. And so you might have a negative feedback loop, and this stabilizes as it reduces the change and returns any system to the original state. So an example of this is seen in predator-prey populations. So if the rabbit numbers dip, then the fox numbers dip because they run out of food. Then there's less rabbits eating the foxes, the less foxes eating the rabbits, so the rabbit numbers increase, and then the foxes numbers will follow and increase because they got more food, but then the rabbit numbers decline, so the foxes do. So one follows the other. As one increases, it allows the other to increase. As one decreases, it causes the other to decrease. So that is a stable example of equilibrium, because it will constantly keep going back to of equilibrium. However, there is something called positive feedback, and that can cause destabilization to occur. So destabilization would be when this doesn't happen. So instead of reversing the change, something can continue the change and cause that change to happen more. So an example of this could be if your body gets too cold, the enzymes stop working in your body, and that means the reactions slow down even more, and that cools your body down even more. And that's a dangerous position. Now, many people have argued about climate change when it comes to this, and whether climate change is part of a negative feedback, which causes stable equilibrium, or whether it is positive feedback, which causes dangerous, unstable equilibrium. So if you look at these two pictures, we'll talk through why it might be one thing or the other. So this picture suggests that climate change is controlled by something called negative feedback. So the fact that the Earth is going to detect, think about Gaia theory, it's going to detect a change in the temperature, and it will have natural systems to decrease this change and take it back to the original temperature. And this means that it would be more stable, and maybe we don't need to worry as much as we feel we do about climate change. So if we look at this and go through it, you'd be expected to be able to talk about this in an exam. So rising global temperatures may cause the ice caps to melt, but the ice caps have obviously a cooling effect. If the ice caps melted, then there would be more water available on the planet for evaporation. That would create in turn more clouds, and the clouds would reflect more solar radiation, so less heat would actually come into the planet in the first place. This then could cause a decrease in global temperatures. So the increase initially has led to the decrease finally. So that would be an example of negative feedback and causing a stable type of equilibrium. So again, back to that sort of model with the dip that we had here. The climate gets too hot, the Earth will reverse it, and it will cause it to cool back down again. However, some people worry that the climate change is on a positive feedback loop. And the positive feedback loop would cause significant problems, because that would mean that we are in part of a unstable equilibrium. So positive feedback here is going to be an issue in this case. So let's go through this one. We've got rising global temperatures. That again causes the ice caps to melt. But if we look at that, what that would then do is expose a lot of dark soil, because the soil underneath the snow is going to be dark. The snow and the ice before it has been reflecting a lot of heat because it's light. Also, the deep sea beneath the Arctic and the Antarctic would be exposed, and that's a dark colour, also dark blue also, which would absorb lots of heat. This means more solar radiation would be absorbed, and therefore there would be a drop in the albedo, which means a reflection of heat, and therefore the temperature would continue to rise, and then that would make it worse, and it would continue to get higher and higher and higher. So then, is there any resilience to this? Well, depending on the ecosystem that we're talking about, some ecosystems have resilience due to the fact that they have stuff like a high complexity. So the ability of a system to return to its original state following a disturbance is what we mean by resilience. Okay, and resilience helps maintain the stability of a system. So you may remember hopefully an image like this. And here we have this idea of the ball again, and it's got a high curve either side. So if I released the ball from here and it went up to here, it should be enough that it would go back. So if we change the conditions of the Earth to a certain point, or an ecosystem to a certain point, the ball should roll back to the middle, the conditions should return, the Earth would return it back to normal. However, there is always a certain level. So if I took the ball and dropped it from way up here, it might go over the threshold into the new dip, into the new conditions, and it wouldn't be very easy to get it back at all. And this represents the idea of climate, for example. If we push our climate too far, will we go over a climatic threshold, which means that it will go to a new equilibrium position, a new maybe hotter temperature, and then it'll be very difficult to push that back to the original condition that we much more are adapted for. Make an ecosystem more resilient, and the list here is the key things that you need to be able to explain. So an ecosystem that is more biodiverse, has a higher biodiversity, will have a higher resilience, because if one species goes extinct, another one will fill its niche. An ecosystem with a greater genetic diversity within individual species will have a higher resilience, because it means they'll be more able to adapt to change. A species with a larger geographical range will have more resilience, because they'll be able to survive if an area gets damaged, habitat gets destroyed in one area. When there's a larger ecosystem in general, there'll be a higher resilience. When the climate is steady, which means it's stable and it doesn't change very often, that will provide a higher resilience, because you won't have to adapt to change. Species reproductive rate can have an impact on resilience, so animals that reproduce quicker with larger numbers are more likely to be resilient than animals that take a long gestation period and will produce very few offspring. And human involvement can obviously make an ecosystem get damaged, but it can also increase the resilience if we manage it correctly. So this is known as a tipping point, and if an ecosystem has enough change leading it to a new state, there is significant changes. There'll be significant changes due to biodiversity, because that condition will maintain itself. And the example where you may have been told about this before is in coral reefs, and this is leading to coral bleaching. So coral reefs have been largely damaged over the last few years by coral bleaching. The idea that ocean levels of acidity are rising, and at a certain point, if the oceans keep absorbing carbon dioxide, they will develop more and more acid. So the reason the oceans are getting more acidic is because of carbon dioxide gas, which dissolves into the water to make carbonic acid. Now that carbonic acid is adding to the acidity, which is dropping the pH level of the water, and at some point scientists are worried that the water may go over or below, I suppose, a pH threshold, which will mean then that all the coral starts to bleach in the ocean, and it will take us to a new level which will be very difficult to come back from. So when coral reefs die, as they go past that threshold, it's very, very difficult to regenerate it. And often they also become covered in algae as a result. So here you can see two different things just for you to sort of see. This is an example in Jamaica where there is a coral dominated system, but due to all of these impacts of overfishing, nutrient runoff of fertilizers causing eutrophication, sedimentation, disease outbreaks, the damage of hurricanes damaging the coral, all these things are pushing the coral in certain areas across tipping points, and as a result then the life, that basically the habitat dies out because there's less coral, then there's less fish as a result, and less things like urchins as a result, because then algae then outcompetes the coral and it kills off the coral. So those are examples of tipping points that have been seen. And you see here that different percentages hit, and we think 30%, when the fish biomass drops to 30% of what it currently is, then the coral tends to become an algae-dominated system. So a definite example of studied tipping points in coral sea. And we obviously are worried about this on a global scale, that we're hitting a climate tipping point, and all of these things are heavily interconnected. So in the Amazon rainforest, for example, we are seeing droughts, and if we worry that if they have too many droughts, that will actually make the rainforest run out of water, which means it can't replenish its own water through transpiration, which means it won't be a rainforest anymore, it'll just become a forest, and that will have devastating effects on the biodiversity there. But this all sorts of starts with the loss of Arctic sea ice. The Arctic sea ice then causes the slowdown in circulation, and we're seeing the tide and the currents in the sea decrease. That then is having impacts on ice loss, because cold waters aren't necessarily moving as they should be around the planet. The Arctic is also causing permafrost to be lost, which means more methane is being released. So all these things are interconnected, and we think that the world has already crossed up to 9 tipping points that could lead to catastrophic climate change. And that's why fighting climate change is urgent and not something that can be left into the future, because it would be hard to get it back to the original point of equilibrium.